Alright, for this video we're going to be setting up our electrolytic cell or electrochemical cell. So these are voltaic cells. So we're going to make that right now. And to do that, we are going to first look at what the metals are that we're using. So we're using a silver-lead cell. And the next thing I'm going to do is I'm going to go look up the potentials for that silver-lead cell on the chart. So I'm going to look these up in the reduction potential chart. When I look at the reduction potential chart, I'll find that there are two values here, one for the lead, one for the silver. The reduction potential of the silver is higher than the lead. The lead has a value of negative 0.13, and the silver has a value of 0.8. The most positive potential, or we can think of this as the strongest reduction potential will dominate. So in this case, this is stronger. 0.8 is greater than negative 0.13. So this is the reduction. And this one will change to oxidation. Okay, so in which cell does reduction occur? So when you go to set this device up, you're going to have two little buckets of liquid, and you're going to put two pieces of metal in that bucket of liquid. One of those will be silver, one of those will be lead. One of those will form the anode, one of those will form the cathode, and that will be determined by this voltage. So in this case, we have a silver that's the most positive one, so that's where reduction will occur. So reduction, so the silver will be reduced, So that's going to form this cell over here. This we got the Ag here. We put our Ag ions, and these ions are going to go in this direction. I'm just going to switch colors here. So these Ag ions are going to become the Ag metal that makes up this thing. This is reduction. Reduction occurs at the cathode, the red cat. Reduction at the cathode. So this is our cathode here. And also, because reduction is going to be important to this, it's going to need a supply of electrons. So those electrons are going to have to come from somewhere, and we can put whatever we want up here. Sometimes we put a meter. Sometimes we could even put a little light bulb if we want. Whatever you like. We're going to need those electrons, and those electrons are going to come from our sacrificial metal, our metal that's going to be oxidized. So the metal that's going to be oxidized, so our reduction, here we've said that the reduction will continue to be the silver, one electron, which gives us silver metal. And then the oxidation has to be something that produces electrons, right? So we have to have something that makes electrons. Well, the two reactions I placed at the top of the page do not produce electrons, but if you took this reaction and reversed it, then you would be able to produce some electrons. And that's exactly what we're going to do, is we're going to reverse that lead reaction and make it into an oxidation. Now these values up here, these were the reduction values, right? So I'm going to also make a little point about talking about these. The reduction value here is 0.8. But now I said this is an oxidation. Well, oxidation has the opposite value to the reduction. So previously it was negative 0.3. Now it will be positive 0.3 volts. And that means that the entire cell, perhaps I'm going to use my zoom here, the cell is going to be the addition of these two, 0.93 volts. And the net reaction of these two, which is not dependent on how many times the reaction occurs, is going to have to be multiplied for the silver so I can balance out the electrons. And I'm going to get 2 silver ions plus 1 lead produces 1 lead ion plus 2 silver metals. And those electrons cancel out because we have 2 electrons on both sides. Both the silver producing 2 electrons and or using 2 electrons, the lead producing 2 electrons. So which metal is the anode? Well, the anode is anox. So anox. The anode is oxidation. Anox. So that means the oxidation is the lead that we just labeled. So that will be lead is the anode. And let's go back and put the lead in here. Put the lead bar. Put the lead 2+ ions. And they are being formed. So as the lead falls off the bar, it is releasing electrons down the wire, and those are continuing. Now this solution on the left here, this solution is getting more positive, right? The amount of positives are increasing. This solution, the positives are leaving. So we can think about positives are going down. So we need something to balance that. That is what we call a salt bridge. It's usually a piece of paper or a tube filled with liquid. And this tube will have inside of it some sort of ion. In this case, we could think that it has maybe some potassium chloride. How about that? So the potassiums will go down this side of the tube and try to fill in the charge that's missing from those silver ions leaving. And the chlorine will move down this tube to counter the extra lead that's formed. So which directions are the electrons moving is our last question. The electrons move from A to C, or from anode to cathode, just like the alphabet. Or in this case, from lead to silver. There we go. And that covers us for everything. We have lead that is being oxidized. We have silver ions in solution that are being reduced. And the electrons from that lead anode is moving to the cathode. Maybe a little bit more labeling could be done up here. Anode. There we go. Okay, and that's that. So identify which one has the most powerful reduction potential, the most positive reduction potential. Invert the other metal half reaction to be an oxidation. Change the sign so that it's not the electropotential of reduction, but the electropotential of oxidation. And then add everything up, and you're golden. We can put little zeros here because these are standard. Okay. Good luck, and we'll talk to you later.